The overall goal of this procedure is to prepare and test half coin cells for laboratory research. First, prepare a working electrode, a counter electrode, and other cell components. Then, meticulously assemble the coin cell in a glove box and seal by crimping. Finally, perform electrochemical testing of the coin cell to determine its key properties, like the charge and discharge capacities, rate capabilities, and other valuable coin cell information.
Generally, cell construction is challenging because the performance of the cell is highly sensitive to the construction procedure.
First, prepare an NMP binder mixture of approximately 6 weight % PVDF binder in NMP. Next, mix the active material and C-Black by Vortex for 1 minute. After adding some NMP binder mixture, transfer the ingredients to a small glass vial. Vortex the sample at maximum RPM for about 30 minutes. If necessary, add 2 zirconia balls of 5 mm diameter for better mixing. Continue to add NMP as needed to obtain a slurry of required consistency. Next, spread a metal foil of the current collector onto a glass plate. Aluminum is used as the current collector for the cathode, and copper is used as the current collector for the anode. Use acetone and remove any air bubbles between the foil and the glass plate. Now, position 2 layers of masking tape to define the region to be coated. With a stainless steel spatula, apply the slurry onto the metal foil. Spread the slurry uniformly onto the track using a razor blade. Depending on the material and binder used, dry the coating in air or vacuum at approximately 90 to 120 degrees Celsius for about 2 to 8 hours. After cutting the dried coating, place the coated metal foil between 2 steel plates lined with 2 weighing papers to protect the coating. Then, press under a load of approximately 3,000 pounds. Now, punch 8 mm discs of the dried, coated metal foil. Next, weigh the cathodes, wrap them, and place them into the glove box. Also, punch 8 mm discs of the uncoated metal foil of the same material and weigh them. As the electrolyte is photosensitive, store it in a Nalgene bottle wrapped in aluminum foil. Inside an argon glove box, use a nylon brush or stainless steel scalpel to clean the surface of the lithium foil until a shiny, silvery surface appears. Then, punch 12.7 mm discs of the lithium foil. The components of the coin cell case are meticulously ordered. Prepare 19 mm discs of CellGuard C480 membrane for separators. After flushing the exchanger 5 times with argon, transfer the working electrode, coin cell cases, springs and spacers, and separators onto the glove box working surface. To start assembly, add 2 drops of the electrolyte onto the cell cup and position the working electrode. Next, add 3 drops of the electrolyte and place 2 separators with 2 drops of electrolyte between them. Proceed to add 2 more drops of the electrolyte and position the lithium counterelectrode. Now, place the 2 stainless steel spacers and a spring on the lithium disc. Finally, close with the cell cap and crimp the cell 3 to 4 times. Handle the finished cell with plastic tweezers to avoid short-circuiting and wipe off the excess electrolyte. As soon as it is assembled, connect the coin cell to the battery tester in the open circuit voltage mode for 1 hour. Define the voltage window for testing the cell based on the active material used in a working electrode. Now, for the theoretical capacity for this cell, first calculate the weight of the electrode material. Then, compute the weight of the active material in the electrode, and determine the theoretical capacity for the electrode disc. Now, test the coin cell to charge-discharge cycles at the required C rate. In the preparation of the working electrode, it is important to create a slurry of good consistency. These results compare good and bad coatings after drying. Note, a cracked coating typically results from a slurry that has excess NMP, and a porous coating typically results from a slurry that has insufficient NMP. After the cells are assembled, they are crimped to obtain a tight seal to protect from moisture. Typically, a badly crimped coin cell splits open after a few hours in ambient temperature due to the swelling of the lithium foil after reaction with moisture. These data are representative of a coin cell constructed from a working electrode of lithium cobalt oxide and a lithium foil counterelectrode. The plot shows the first charge and first discharge curves for the coin cell. Note, the voltage window was set to be between 3 and 4.3 volts. The capacity was 155 mA per gram for the first charge cycle and 140 mA per gram for the first discharge cycle.
Once mastered, this technique can be used to construct and evaluate coin cells using different cathode materials.
While attempting to this procedure, it's important to remember to keep the work desk as dry as possible.
After watching this video, you should have a good understanding of how to construct and test coin cells.